Hello friends, welcome back to our YouTube channel. If you like this video, please like, share and subscribe. I'll share our videos commanded by our experts, so let's begin.
If you like, please like, share and subscribe. So let's begin our today's topic. Let's begin.
For the last 2 years, inbound traffic from AI chatbots arrived as a fragmented collection of referrals. Clicks were scattered across different categories, obscuring the true scale of generative engine impact. That data is now being forced into a unified stream. Google Analytics 4 has introduced a native AI Assistant default channel group to automatically identify and track website traffic originating from generative AI platforms. This update removes the operational burden of writing complex regex codes or building custom channel groups to filter AI referrals out of standard organic or direct traffic. The platform now provides out-of-the-box detection for major tools, including ChatGPT, Gemini, Claude, and Perplexity. This native categorization provides a transparent look at Generative Engine Optimization, moving these sessions out of the untrackable dark social categories and into a dedicated reporting line. The value of this update lies in the fundamental difference between traditional search behavior and the targeted approach of Generative Engine Optimization, or GEO. While traditional search is a broad, discovery-led process, GEO specifically targets users who have already refined their queries within a chatbot. Currently, AI traffic is a small fraction of traditional search volume, but conversion performance shifts. Early reports show the AI Assistant channel spiking above organic search in key event rates. These users show stronger intent, completing research within the AI interface before clicking through. Proving this ROI for a specific business requires more than a standard report. It requires a custom exploration to isolate the high-intent variables of AI traffic. To build this report accurately, we have to look at the underlying mechanics of GA4's detection, the HTTP referrer string. The process begins when a user clicks an inline citation or a link within a web-based AI chatbot interface. That click generates an HTTP request. The source domain, such as chatgpt.com, is packaged directly into the request header. As the request arrives, the GA4 logic engine scans the referrer string to identify the point of origin. The engine evaluates this data against a native lookup table that maps known generative AI domains. If a match is found, the session is automatically assigned the AI Assistant medium label and sorted into the corresponding channel. This is an automated process that identifies traffic without the need for manual UTM parameters or custom channel grouping. However, because the system is built entirely on the successful transfer of referrer data, it contains a significant blind spot. This blind spot involves native mobile AI applications and integrated API tools, where data passage is not guaranteed. When a user clicks a link inside a native mobile application, the platform may fail to pass clean referrer data, leaving the string empty. In these instances, the logic engine finds no identifiable source, and the traffic falls back into the direct bucket. Analysts must remain aware that until detection mechanisms for mobile environments improve, certain geo conversions will remain hidden inside direct traffic anomalies. To extract actionable insights despite these limitations, we must engineer a custom exploration dashboard to compare this traffic against traditional search. In the GA4 Explore section, we start by creating a new blank report canvas. In the Variables column, we first import our dimensions, Session Default Channel Group, and Session Source/Medium. Including Source/Medium allows us to later break down performance by specific platforms, like comparing ChatGPT's conversion rate against Perplexity's. Next, we add our foundational metrics, sessions and engaged sessions. To test our geo hypothesis, we also include intent-based metrics, engagement rate, and session key event rate. Session key event rate is the primary metric for this analysis, as it reveals the percentage of users who took a high-value action. With these dimensions and metrics loaded into the variable bank, the statistical components are ready to be mapped to the canvas. To structure the report, drag Session Default Channel Group into the Rows section of the tab settings. Then drag all 4 metrics into the Values section to populate the data table on the right. At this stage, the table is cluttered with every default channel, social, email, and referral, making a direct comparison difficult. To clear this noise, we must apply an isolation filter. In the filter settings, select Matches Regex and enter the string !, open parenthesis, AI Assistant, pipe, organic search, close parenthesis, $. This specific command tells GA4 to display only these two rows, excluding all other traffic sources from the comparison. The table now refreshes, stripping away the irrelevant channels and leaving a clean side-by-side comparison of organic search and AI assistant traffic. This isolated environment is the required baseline to accurately measure the return on investment for generative engine optimization. The output of this report immediately highlights the volume disparity. The sessions column shows traditional search remains the primary traffic driver. However, in the performance columns, the data reverses. The engagement rate and session key event rate for AI assistant sessions are significantly higher. This performance premium is driven by user intent. These visitors have already used a generative engine to synthesize information, meaning they arrive at the site further along in their decision-making process. The AI referral click is a late-stage action, representing a highly qualified user rather than a casual browser. Analysts should save this exploration to monitor the maturation of AI traffic on a month-over-month basis. As the adoption of generative engines scales, the absolute volume of the AI assistant channel will likely grow while maintaining its high conversion efficiency. During this transition, it is critical to maintain vigilance over the direct traffic category. Until referral data from mobile AI applications becomes more reliable, much of the true GE impact will remain masked within direct traffic anomalies. GA4's attribution mechanics move GE strategy out of the theoretical realm. The financial impact of AI visibility is now isolated, quantifiable, and ready for optimization.
Over the last year, a distinct source of inbound website traffic emerged: citations embedded directly inside AI chatbot responses. Because these diverse AI platforms use vastly varying protocols, this new web traffic arrived completely fragmented, effectively clogging the mechanics of standard attribution. To isolate these AI referrals from organic or direct traffic, marketing analysts were forced to write manual regex codes, lengthy strings of text designed to hunt down and group specific URL variations. Google Analytics 4 recently addressed this by rolling out a native AI assistant default channel group. This interface comparison shows the shift in reporting. On the left is the manual methodology of custom regex strings. On the right, the new reality: a single table row integrated natively into standard acquisition reports. Out of the box, GA4 now automatically maps inbound clicks from major generative AI tools, recognizing platforms like ChatGPT, Gemini, and Claude, and engines like Perplexity. This update replaces the need for custom channel groups. It standardizes the detection process, allowing analysts to monitor AI referrals without manual intervention. However, treating this single channel as the total sum of a website's AI traffic ignores the structural limitations of how web data is actually passed. Visibility inside generative models is a field known as Generative Engine Optimization, or GEO. It relies on different visibility principles than traditional search engines. Despite the new native tracking, a massive portion of GEO traffic remains completely invisible to the AI assistant channel. To find the missing data, we must deconstruct the specific technical mechanism GA4 uses to classify these clicks. The tracking architecture works for standard browser environments, but it fails in two areas: native mobile applications and API-integrated tools. Identifying where these tracking failures occur is the only way to accurately calculate true geo return on investment compared to traditional search. Web analytics depend on an origin reporting protocol. When a user clicks a link, their browser communicates its previous location to the destination server. When a user clicks a link inside a chat interface, an HTTP request packet travels to the destination server. Inside is the HTTP referrer header, containing the source domain URL. Reaching the server, GA4 scans this string. Recognizing domains like chatgpt.com, it stamps the click with the AI assistant label. This evaluation occurs strictly when a user clicks a link within a web-based chat interface. Because the system relies on the presence of a clean referrer string, it is extremely fragile. Referrer-based tracking is reliable for traffic moving between browser tabs. Once a user moves outside the browser, that data stream becomes vulnerable to being stripped. Early performance data already shows why isolating this traffic is a priority for analysts. Comparing total traffic volume, AI referral traffic accounts for a tiny fraction compared to standard organic search. However, when we switch to key event conversion rate, the AI assistant bar surges well past organic search. Visitors arriving via AI assistants demonstrate stronger page engagement and higher conversion intent than those arriving from standard search results. This high intent forces a change in how marketers value a citation. A single AI-driven click can be more valuable than multiple traditional search sessions. Because the conversion rates differ so significantly, analysts must use custom exploration reports to track GA4 independently. The high value of these users exposes the flaw in GA4's tracking architecture. If the HTTP referrer tag is missing, the GA4 scanner has no data to evaluate. It cannot assign the AI assistant label to an anonymous click. There are two specific environments where this referrer data is effectively destroyed: native mobile applications and integrated API tools. This Sankey diagram shows two paths. Web-based chatbot data flows smoothly into the green AI assistant bucket, but native mobile apps hit an architectural barrier as the operating system scrubs referrer data. Custom APIs also lack referral headers. Stripped of identifiers, these clicks bypass AI classification, rerouted into the massive direct traffic bucket. This creates a hidden stream of data. Like a subterranean river, it carries significant volume, but remains invisible on the surface of your reports. GA4 handles unidentified traffic through a standard fallback protocol. It defaults everything it can't verify to direct. This means high-intent geo conversions are frequently mislabeled. They are currently masquerading as untrackable direct traffic. The GA4 update successfully isolates a highly engaged user segment, provided they use a web browser. However, the data in the AI assistant channel is a baseline, not a comprehensive total. This adjusted acquisition report shows how to interpret the data. The green AI assistant row is verified, but the direct row now requires an analytical asterisk. Marketers must treat the AI assistant metric as the absolute floor of their AI traffic volume. Mobile and API stripping ensure it will never represent the actual ceiling. While detection mechanisms may eventually improve, these structural gaps remain a permanent feature of current tracking protocols. Analysts should treat sudden, unexplained spikes in direct traffic with skepticism, especially if they correlate with mentions in generative AI platforms. Effective analysis relies on architecturally understanding what a dashboard is incapable of measuring.